Good morning. I'm Andrew Ferguson, and today I'm going to talk about participatory networking. It's our API for application control of SDNs. This is joint work with my great colleagues, Arjun Guha, Chen Liang, Rodrigo Fonseca, and Shriram Krishnamurthy. Now, participatory networking integrates end users and their applications directly into the management of the network. As a motivation, let's consider 4 applications which might like to manage the network. The first is SSH Guard. SSH Guard runs locally on end hosts and monitors the access logs for repeated failed SSH login attempts. In response, it installs local firewall rules in order to block this traffic. Now, if it could manage the network, SSH Guard would prefer to deny the traffic as close as possible to the source instead of locally on the end host. The second application is Akiga. Akiga is an open source voice over IP client. It creates paths through the network in response to phone calls that are initiated by the end users. If it could manage the network, Akiga would prefer to install QoS rules to provide users with excellent quality for their voice and video calls. The third application is Zookeeper. Zookeeper is a Paxos-like coordination service commonly found in data centers. In Zookeeper, several servers are spread across the data center, and they exchange small control messages in order to maintain consistent replicated state. Now, Zookeeper would prefer if these control messages could be sent through high-priority queues in order to prevent them from being delayed by any large elephant flows also transiting through the network. Finally, Hadoop. Hadoop is an open-source, MapReduce-like data processing platform. In Hadoop, multiple jobs run concurrently throughout the network. These jobs have different weights, which provide a level of priority. The weights are used to provide CPU and memory resources for the jobs in accordance with the weights. But Hadoop, if it could manage the network, would prefer that these weights also be expressed along the network paths. Well, how could we do all of these things today? We perhaps could file tickets with our network operators every few minutes and have them change the network configuration according to their dynamic needs. These needs, because they change so frequently, preclude a single static policy. Well, maybe instead of that, we could use an SDN controller for each of these applications. However, combining these controllers would be difficult. Each would be running effectively as root, and their decisions would affect one another. This situation sounds like chaos. Well, if we step back for a moment, we see there are 2 challenges here. The first is how to decompose control and visibility of the network, and the second is how to resolve conflicts between the different requests. Or in other words, how do we prevent every application from needing to run as root on the SDN controller, and how do we keep these programs from affecting one another? Participatory networking is the approach we developed to solve these 2 challenges. To do so, we need to reason about how changes are being made in the network. Now, to make such reasoning tractable, we don't allow general-purpose programming. Instead, we provide our applications with a restricted control plane API. In our API, users, their hosts, and their applications send 3 types of messages to a logically centralized network controller we call pane. The first are requests for resources, such as guaranteed minimum bandwidth, latency, path properties, or access control. The second are hints about future traffic. And the third are queries for current or future properties of the network. Now, the pane controller serves as an arbiter for any conflicting proposals, and then ultimately performs the requested reconfigurations on behalf of the users and applications. Participatory networking introduces an end-user API, or set of system calls for software-defined networks. It's not proposing any new mechanisms for network resources, such as QoS, or for access control or routing. It's simply allowing the end users and their applications to make use of those already there. Now, unmodified applications, or those which choose not to participate in our system, simply continue to receive the same best effort performance of existing packet networks. Now in our vision, the network operators will set a baseline policy that enforces fairness and security, while allowing the end users and their applications to propose new configurations to meet their unique individual needs. So let's begin with the first challenge. How should we decompose control and visibility over the network? So to divide authority, Payne uses a hierarchy of network shares, which describe who can say what about which flows in the network. First, each share has a list of principals, who are the end users and applications authorized to use this share. Second, each share refers to a particular flow group. It's a set of traffic flows identified by the standard attributes we find in networks, such as source and IP MAC addresses, protocols, and port numbers. Finally, they have a list of privileges, indicating what can be performed using this share. Now, for example, traffic can be allowed or denied. Its bandwidth can be limited or provided with a guaranteed minimum. We can also waypoint traffic through particular switches and avoid links which we'd like to avoid. Shares also authorize our end users to issue the hints or make queries about particular flows within the shares flow group. These actions can also come with additional restrictions. So for example, we restrict bandwidth reservations using a token bucket model. Now, a share's principals also have the capability to delegate privileges by creating subshares. The creation of subshares is guided by the principle that you can't give away more authority than you have. So for example, a share's flow group must be contained within the parent share's flow group. Here, this blue bar represents the range of source IP addresses used by that share. Furthermore, a subshare may not have a more permissive action set than its parent. Here, the parent share is capable of reserving up to 100 megabits per second of bandwidth, the child share only up to 50. Initially, the share's only principal is the root user, and then any additional users can be added. The process of creating subshares creates a share tree, a whole hierarchy of shares. At the root of the share tree is the root share, a share which contains all flows in the network, contains every privilege, and has the network operator as the user. The share tree only sets the static context for configuring the network. The actual configuration is performed by the requests and hints, which come dynamically to the Payne controller. For example, requests describe an action the principal would like to perform on a flow group during the given time interval. This one is to reserve 2 megabits of bandwidth over the next 5 minutes. After evaluating the request, the Payne controller returns an immediate response indicating an accept or reject. Hints provide information about current or future traffic patterns, such as traffic being short and bursty. Now, the Payne controller is not required to respond to this hint and may optionally choose to reconfigure the network in response. Shares also provide principals with the right to issue queries, perhaps to measure web traffic over a previous time interval. And all of these must be contained within the flow group on the share. To keep things simple, I'm going to focus on requests for the remainder of this talk. You can find further details about the hints and queries in our paper. Now, by design, a share's resources may be oversubscribed by its subshares. So for example, a share here which is permitted up to 100 megabits per second of guaranteed bandwidth may permit each of its subshares to make similar reservations. Now, in order to ensure that these restrictions are never violated, new requests are recursively evaluated up the tree. So for example, the user of share A makes a request for 80 megabits per second of guaranteed bandwidth. The Payne controller, seeing no existing requests, will accept it, and then account for this reservation all the way up the tree. Later, when a user of share B makes a reservation for 50 megabits per second, this reservation request is rejected in order to prevent a violation at the root share. Finally, when accepted requests become active, the pane controller uses OpenFlow to reconfigure the network and implement the desired requests. Let's turn now to our second challenge, how to resolve conflicts between requests. For this, we developed hierarchical flow tables, or HFTs. Now in pane, we have two hierarchies. The first, the share tree, you already saw. It sets the static hierarchy of privileges granted to users and applications. This hierarchy, in essence, sets the stage for a dynamic hierarchy of policy requests. As users and applications make requests, these policy trees evolve, always within the bounds set by the share tree. Now, following the ethane model, we imagine that every packet in the network is processed against a global policy living at the central controller. For us, packet processing is the result of using the current policy tree applied to this packet. Now, first, we identify the matching policy atoms, highlighted here in green. These policy atoms emit their actions. When multiple subtrees have produced actions, we need to apply user-defined operators at each node in the tree to combine their actions. Here, a +S sibling operator is used. Next, we combine the children's actions with the parents using a +P parent operator. In this case, the parent did not have any action, and we denote this by a 0 don't care identity value. This process continues up the tree until a final action is emitted. At this stage, we see two policy atoms within a single node that apply to this packet. These are resolved with our third operator, +D. When a final action is emitted from the root of the tree, that is the action applied to the packet. So participatory networks use these three combination operators within each node to resolve conflicts. We saw the first is the +S operator, combining sibling actions. The second, +D, resolves any multiple actions inside a single node. And then finally, +P is applied to the resolved actions of the children and the parent. Now, the requirements on these three operators are very basic. They must be associative. And this allows us to resolve conflicts in a pairwise fashion between actions. And second, they must support the 0 don't care action as their identity. With these two minimal requirements, we can actually convert the HFT into an efficient implementation, as I'll describe later. Now, the conflict resolution operator's flexibility actually creates a whole design space for this system. This slide is a summary of the choices we made for pane. Now, in Sensible, we strive to combine both requests. So for example, a request to guarantee a minimum level of service may be combined with one that rate limits below a level above that. In other cases, we need to decide a single outcome. So for example, pane's +D and +S operators implement a basic security policy in which deny requests override allow requests. We also take the maximum of two conflicting bandwidth guarantees and the minimum of two conflicting rate limits. The specialization of the +P operator allows pane to implement a child overrides parent model for access control. Now the HFT itself, remember, is agnostic to the specific policies we chose for these operators, as long as they satisfy those two previous requirements. So for example, we could develop additional operators that might resolve conflicts using a priority scheme. So, how do we implement this whole system? Well, in an ideal world, we could simply pass each new HFT to the switches, and when the packets arrive, the switches would evaluate through the tree, just as we did on the previous slides. As you know, today's switches aren't capable of performing these actions. So therefore, rather than send every packet to the controller, we developed a compiler which linearizes an HFT instance into traditional flat open flow match action tables. These are collectively equivalent to the logical policy tree. Now this compilation process is quadratic in the size of our tree, and you can find the details about this in our paper. So our OpenFlow controller installs these tables on the switches, allowing the network to implement the HFT policy with hardware support. Our compiler functions in 2 stages. In the first stage, it linearizes the HFT into a single table we call the network flow table. Now, if the network were connected by a single big switch, we might install this network flow table directly on that switch. So then in our compiler's second stage, it translates the network flow table into individual flow tables for the distributed open flow switches. Now, during this stage, the compiler makes extensive use of our network information base, or NIB. The design of this NIB is inspired by the ONNX work, and it describes the state of the network, including host locations, link statuses, queue availability, switch configurations, and more details. The NIB is also used for answering the queries I mentioned earlier. So for example, the compiler uses the NIB to implement a bandwidth reservation by finding a circuit through the network. It then sends the commands to create necessary queues, and finally the open flow tables to implement the necessary forwarding decisions. This NIB also allows Payne's compiler the freedom to choose where in the network to implement the given policy. So in this simple experiment, we had 2 clients communicating over a wireless link, and one of them was attacked. The transfer rate dropped to only 5 megabits per second, and when a local firewall rule was installed, we saw the transfer only recover partially. Instead, when Payne was used to install the firewall rule, the Payne compiler chose to put this rule as close as possible, and the transfer fully recovered. Even better, when the attacking host moved, the rule moved with it. Now, updating this NIB is the responsibility of our OpenFlow controller. Any updates are propagated back into our compiler service, and the compiler then constructs a new set of OpenFlow tables which continue to implement the decisions of the network-wide flow table. Seen this way, you can think of the network flow table as a set of invariants which our second stage of our compiler service is trying to maintain. So we've been running several prototype Payne-controlled networks within our labs, and they use several hardware and software switches. It provides our day-to-day connectivity for development and other internet applications. So we've also adapted all 4 of the applications I discussed earlier to use Payne. Kiga and SSH Guard simply use our basic ASCII protocol, whereas Zookeeper and Hadoop actually use an object-oriented Java library we also developed. I want to briefly take a look at the Hadoop case. So in Hadoop, we ran 3 sort jobs which communicate in an all-to-all fashion. 2 of these jobs were provided with 25% of the cluster resources, and the third high-priority job was provided with 50%. Our network consisted of 22 hosts, 20 Hadoop slaves plus 2 masters, connected in a star configuration to a hardware OpenFlow switch. During runtime, Payne dynamically was used by Hadoop to create QoS rules to protect the high-priority flows. When we did this, we saw that the high-priority job sped up by 23%, while the lower priority jobs actually sped up by 9% as more resources were freed more quickly in the cluster. Well, let's take a look at the effect of Hadoop on the number of rules created in our switch. If we look at the lifetime of the job along the x-axis, and the number of rules installed by Hadoop via Payne along the y-axis, we see that this never exceeded 30 rules, despite the number of hosts. Our switch could support just shy of 2,000 rules, and we believe this makes this approach feasible. So in conclusion, Payne is designed for applications and users that know what they want from the network. It provides a way for these applications to talk back to the control plane and use any mechanisms exposed there. So far, we've explored bandwidth, access control, routing, and rate limiting, and we hope to support new mechanisms in the future. Second, Payne allows all of these application requests to coexist within a single network by deterministically resolving conflicting requests into a single global policy. I'm happy to take your questions at this time. or you can contact my collaborators as well. Thank you for listening.
Questions?
Well, I have a question. Why couldn't you need all these applications starting on the controller side?
Pardon me, what was the, can you repeat the first part?
Why do you believe that all these application stuff should be on the controller?
Instead of,
As such, should run on the controller side.
sure. So the question is, why do all of these applications need to be involved with the controller? Okay. So one reason, I believe, as opposed to, say, at the end host, hypervisors, one reason might be because we don't trust the end host necessarily. If this is like a user-provided device, we'll trust, we can enforce the policy at the central location with the controller and the switches.
But, for example, let us consider as an example SSH service. SSH is a service between two endpoints. There is nothing for control. So, control plane should not interfere
Sure.
in
So,
the communication of two endpoints.
definitely.
So,
So,
why we should put this on a controller side?
yeah. So,
There is a big danger from the security point of view to mix control plane and data plane and let data plane to be on a control plane.
sure. So this is why we use a very restricted API for allowing our applications to contact our controller. And we believe that because of this restricted API, we're able to analyze it and build a system that checks for any requests that are coming through.
Can you guarantee that there is no code in your interface or on the security plane?
So there isn't any code. It's just a set of API, and we actually have a mechanized proof that shows that what we produce from our API produces valid OpenFlow configurations that can be checked using perhaps other tools. But maybe we should talk about this more later. Gio.
Hi, Jiao from UAC. This is a great talk. Just
Thank you.
have two quick questions. One is, do you have any thoughts on other type of resources that you can handle in this general framework, and how does that change your network? And second question is the scalability thing. Because the evaluation cases you show is relatively a small testbed thing, and how does that scale to larger cases?
Sure. So the first question is about other resources that we might have. So the first one that jumps to mind immediately is latency, right? So we have bandwidth, and like, what could we do about latency? We haven't given a tremendous amount of thought to latency yet. It's a hard problem to see how to combine that, but I do have two thoughts. The first is about if we consider latency as the number of switch hops that we're using within our network. For flows that want lower latency, we might keep them of a fewer number of switch hops. And the second is we are interested in hierarchical fair service curves, which provide a way to combine bandwidth and latency into the queuing model. And so the second question is about scaling. It's a great question. So for the Hadoop case, that was part of it, was like looking at the number of rules that would need to be created by running a real job. We saw that it wasn't sort of quadratic or anything like that. But yeah, more work to be done. This is like a prototype, and the piece was about how do we resolve conflicts and things.
Andrew.
Hey, Theo.
How are you?
I'm good.
Good talk.
Thank you.
We talked yesterday from Berkeley that talked about tuning Hadoop. It was called SIGCOMM. And that's how they talk about having your application actually as the network or a certain things for efficient placement.
Yeah.
I noticed your API was very hungry. It's basically just me saying, I want this. How would you support something like SIGCOMM? And do you think something like SIGCOMM is efficient or necessary to gain?
Yeah, so I think I really want. Oh yes, absolutely. Sorry. Yes. So the question is, how would we integrate, say, something like Sinbad presented yesterday into this approach, especially since it has more of a two-way conversation rather than like, this is my demand, yes or no. And I definitely want this to be a way where we can combine the different requests for systems that have been developed, including like your own micro TE work. I think would be a good one, as well as co-flows. These are, how can we provide sort of access control and conflict resolution for any of these systems? So I see that, and it's great extension place, yeah.
All right. Thank you, Andrew.